Solve the lead code problem, binary tree paths. So this problem is categorized as a common Amazon coding interview question. For this problem, you'll be given a root of a tree and you need to find all the paths from the root all the way to the leaf nodes. So here, for example, there are two paths to the leaf nodes. One is 1, 2, and 5, and the other is 1 and 3. So they have added that. And the format is also important. It should be, each node followed by an arrow mark pointing to the other node all the way to the end. So the output would be a list of strings and the input will be the root node. So given this, there are many ways to solve it. The easiest way I see is using recursion. So when you're trying to solve it using recursion, what we could do is we could visit each node and check if it's a leaf node. A leaf node is the one with no children. So when we reach all the way to leaf node, all we have to do is just return a list. Else, we recursively go left and right, and we keep doing it until we have visited all of the nodes in the tree. So yeah, let's try coding the solution. So we'll just create a helper method to call it recursively. And inside the helper method, we just need to pass three values. So I'll just say by tree traversal, and we'll obviously pass the root node. Oops. And we'll need to pass two additional values. One is the output should be a list of strings. So we'll just pass a new array list. And then we need to keep track of what's each path is when you're visiting the node. So for that, we'll just create a new string builder. So yeah, let's try creating that helper method now. So the return value will be the same as the parent method. And yeah, just copy this. So it's going to take in three arguments like we discussed, the tree node, and a string builder. So when you're writing a recursive function, there are two things you need to figure out. What's the base case and what's the recursive case? Here the base case is when the root is equal to, the node is null, or we have reached a point where the node has no children. So when we have reached that place, the only thing we need to do is add the current node into the list and just return it. So yeah, let's try adding those two use cases. So first one is if node equal to null, we just say return list. Else, the other thing is if node.left equal to null and node.right equal to null. Here, since we have reached all the way to the leaf, what we need to do is first append the value of the current node into the string builder object. So we just say sp dot then we add it to the list. So list dot and just a return list. So yeah, I think these are the two base cases. Now we need to just determine what's the recursive case. So if you have reached a node which is not one of the children, the first thing is we need to append the current value of the node. So we're going to add sp dot append, and also we should remember the format is the value of the node followed by an arrow mark. So we'll just add that as well. Now there are two ways to proceed. We should go visit the left node and the right node. So yeah, we'll just say tree. I'm just going to copy this. So here we're going to visit the two nodes. So node.left, the current list, and here we can't pass this string builder object because here we need two copies of it since you're visiting the left and the right. So we'll say new string builder. So this is because if you notice, when we recursively visit each node, we keep appending to the value of string builder. And yeah, so if you visit the left and right, we don't want the same copy to be adjusted. We want a new copy of it. So here node.write. And finally, we say return list. So what this does is that all the values get processed, and finally it bubbles up all the way to the top, and that's the value which we return in the method. So yeah, let's try running the solution. Okay, so 2 use cases have passed. Let's try submitting it. So yeah, the time complexity of this solution will be O of n, where n is the number of nodes inside the binary tree, because we have to visit all of the nodes once at least to process the different paths. The space complexity, since we're using recursion, so we are using a stack where each solution is waiting for the recursive function to solve it. So the stack will be of size O of n, where n is the number of nodes in the tree. So the space complexity will also be O of n.